welcome to the 5th lecture. So before we continue down the road with power electronics, semiconductor devices, so let's look at something interesting. Let's take a pit stop. Let's take a detour. Let's talk about a little bit about power. We will resume power electronics, tools, and materials. Electronics, tools, and materials. Guys, these are nothing but tools and materials we use to practically build, test, design power electronics circuits we are here to cover. So in the practical session of our lectures, I'm talking to my UICT students. That is Uganda Institute of Information and Communications Technology, Nakawa, Uganda. So those students, because these lectures are going to be streamed on YouTube for everyone, though I have made them primarily for my UICT students. So we will have practical sessions. We'll have practical sessions other than the e-learning program we are currently running. On the LMS system, the learning management system, we are going to be covering we're going to be having practical sessions. So, and in those sessions, I do not want any learner or student to have issues with tools we have in our labs. So, let's look at them before we proceed. Thank you. So, the very first tools we're going to have, let's start with tools. The very first one is what we call a DMM. This stands for digital multimeter. A digital multimeter. What does this one do? It's a tool used to measure voltage, both DC and AC. So it's a tool used to measure parameters like frequency, capacitance. Some of them even measure inductance, continuity of conductors, continuity of conductors. They measure current, both AC and or both AC or, that is for AC or DC. Which other parameter? Very many more parameters. Resistance, geez, I was forgetting the basics. Resistance is also, it can also measure resistance. A DMM, very basic tool we'll have to look at. It can even test diodes. They can even test diodes. Transistors. If you have to go anywhere with electronics, please, there is no way you're going to progress in that direction without owning first and foremost, owning a digital multimeter, knowing how to use one. There isn't really any way you're going to proceed. Okay, that is tool number one. Tool number two, that is tool number one. Let me write here. Tool number two, a very important one. You may own this one, you may not own it at first because it's a bit expensive. That is what we call a waveform. A waveform generator. Like the name states, This is used to generate waveforms, because with electrical engineering, we're going to be dealing with different waveforms. Whether we are dealing with audio processing, power generation, power manipulation, we're dealing with waveforms. So voltages. So a couple of waveforms. So this device or this tool generates waveforms like the sine wave. We'll discuss why sine wave. We can generate cosine wave. Of course, a cosine wave is a sine wave shifted. A shifted sine wave. There is a ramp, what to call a ramp, a square wave. Square wave can generate electrical noise if you need it, let's say to test a filter, and for other reasons. So, and more. So, I'm just listing a few. A digital multimeter, a waveform generator. Let's look at the third one. Let's look at the third one. Let's look at the third one. This is what we call a DSO. This stands for digital oscilloscope. Digital oscilloscope. A digital oscilloscope, a DSO. These can be used to measure all of these with one interesting feature. It can even be used to look at different waveforms with one feature that stamps it all out, that is graphing. Voltages with respect to time. Very important. What's the voltage doing on the uprise, on the down, throughout the different circuits we'll be looking at. We'll be building circuits, demonstrating them, testing them out, testing out components. The oscilloscope is fit to do just all of that if you know how to configure it. Think of it as a fancy multimeter that has graphing capabilities. So with this section, I'm not going to write much. I'll just demonstrate. Let's kick off the tools list with what we call a digital multimeter, a DMM, right? It's called a DMM in short. So the full name is a digital multimeter. So it comes with a couple of leads to go out and take measurements, a couple of measurements as we are going to explore them, a couple of measurements from the circuit we are currently working on. It could be testing out a component, taking voltage measurements, like I previously mentioned all of the parameters this device is capable of taking. So this is the digital one. If you remember alright, so like we had discussed in the first half of the lecture, so in the first half of the lecture, we had said this device is capable of making a couple of measurements. So let's say we want to take measurements of the voltage of, let's say, a battery, right? Let's say we want to take measurements of the voltage of a battery. So let's say we have a battery on table that happens to hold a couple of volts, right? DC, that's DC. So this is our test subject. So this happens to be a lead acid battery. At nominal voltage, it's around 6.8 to 6.9 volts. That's it. That's if it's fully charged. One way to test it, if let's say we wanted to design a circuit that charges, this battery, so that falls right into the category of applications of power electronics. So for the mode I'm having, let me just turn it on to volts DC. So I'll put it down so that we can easily see them. the voltage readings. So I'll put my negative lead to the battery first, then the other lead as so. So that's the reading we are getting. So it says it has 5.9. So this is almost close to cutoff voltage of this battery. So if we are to deplete this battery any further than this, it's most likely going to get damaged. So how have I determined that? With the use of a tool, a digital multimeter. So that is candidate 1. Let me switch it off. So let's say we wanted to measure the capacitance of such a device, right? Hope it's clear. Yep. So this is a capacitor. This is a ceramic capacitor. So I will turn my multimeter to the capacitance mode, right? So since mine doesn't require to adjust any kind of to make any kind of manual adjustments, it's automatic. I'll just connect my probes. One of them I'll touch it, the other one I make sure I'm not touching it. I'll have to make sure I'm not touching it, so wait a little. For it to have a settled value. So it's saying around 76 something, 70 nanofarads, 0.077 nanofarads. So that's what I'm holding in my hands. So let's say I wanted to test. Let's say I wanted to test the faultiness of a diode. So for mine, I'll have to switch. To the diode and continuity mode. Then switch it over to the diode functionality, right? So guys, I'm making a few demonstrations. So this is what we call a diode. This is a diode. This is a diode. See? So because remember, diode conducts in one direction and not the other. So let's see whether we are getting any values from the multimeter. I'll connect the positive lead to the N side of the diode and the negative lead to the P side of the diode. So we are not getting any values, right? So let me flip the diode around. There we go. We have values. So this diode is fully functional. It does not conduct in both directions. We have this bigger one. This could probably be a Schottky diode, a power diode. This is how it looks like. So this is much bigger than this. Much bigger, right? So these two, you can see the physical difference. So we could conduct the same test. So what I'm holding are what we call the leads. So I think with this one it's a bit clear. So we're not getting any values whatsoever. So let me flip it around. In that configuration, we happen to be getting values. So this power diode is functional as well. So we could go on and on. This is another kind of diode, right? So if I'm to test whether my diode is functional or faulty, just connect the leads like so. If I flip them around and the diode does not glow, I probably have a faulty diode on my hands, a light emitting diode. So we could have more components, right? Capacitors, electrolytic, ceramic. So that's the job of a digital multimeter. So let's head over to the next tool. I'll switch it off. Let's get to the next tool. So this is probably the most important tool in power electronics or any other branch of electronics. So this is what we call the lab bench power supply, right? So why is it called a lab bench top power supply? Because it sits on top of a bench, right? And it's a power supply. It delivers power. It delivers a certain voltage at a specific current limit. What do I mean by that? So let's take a closer look at this device. So this device, this tool, I'll turn it around. So by just simply showing you this, it simply tells you what we are already dealing with, right? Exactly. So its input voltage is around 240, 230 volts AC, but the output is from 0 to 30 volts DC, 0 to 5 amps DC. So what it does is to take in an AC voltage, right? Take in an AC voltage. Its job is to take in an AC voltage and convert that voltage to DC at a different level. So guys, even in the course unit itself, we are going to have power conversion circuits. Long and behold, this is one of them. Only that it's in a bigger form factor and a bit advanced. So when you look closely, we have the voltage and current markings. To the right, we are seeing something else. We are seeing CV. Let me put it a little bit to the sides. So we are seeing CV, that stands for constant voltage. That stands for constant voltage from the voltage side. So we are seeing CC, that is constant current. Okay, it happens to be having a couple of knobs. The knobs, there is the voltage knob. There is the voltage knob. There is the voltage knob, if you can see the word, and there is the current knob. Yeah, the voltage and the current knob. So these are knobs that we can use to adjust the supply voltage, the output voltage that's coming out of its output terminals. This is its on-off switch, right? These are the power leads. These are what we call the power leads, right? Their job is just to connect, to extend the output power to our circuit we are working on. We could be working on something like this. We could be trying to build a circuit. We're going to be building circuits. I will introduce what this is. So we could be powering something, could be powering anything, right? Yeah. So these extension leads, or these beautifully built cables, are what we call leads, power leads, right? So they connect to the device like so. So I will use the yellow one. To go like there, like so, and the ground to go there like so. So from these two outputs, from these two alligator clips, so this is where I clip onto the circuit I want to deliver the power to. So make sure these don't touch. So we have these in the lab. You have these in the lab. So let me make a small demonstration here and be done with this tool. Yes. All right. Let's say I have a DC motor to run, right? And it operates like around 5 volts. So let's say this is the motor we need to power, right? So this is the motor we need to power. Place it there. So let's say that's the motor we need to power, and that device operates at 5 volts. What do I need to do? This is what I need to do. All right, so I will head over to the power supply, switch it on. So remember, this happens when the leads are separate. I must set short or connect these leads together. So I'll place them like so. Make sure they do not touch. So let's get back to the voltage. Let's get back to that. So remember the knobs, I For my specific power supply, I have to press the knob once, twice. First increase that to 5, then I go to the last digit, turn that to a 0. So that's around 5.1 volts. So I need to set the maximum current. Let's say this motor draws, let's say 200 milliamps. That is 0.2. So I need to press again on the current, then turn it down a little, right around there. So what the power supply will do is to make sure it maintains roughly the power. It maintains the power that it can get from 5 volts multiplied by 200 milliamps. So it will adjust the output voltage and the current to make sure that that power output does not go beyond the limit. So let's power the device. Let's power the device. So I'll place it around there. I'll bring my negative lead there, then so hope we can clearly see it. Every time I take off the lid, it goes off. So long and behold, we have seen how we can use our power supply power a DC motor. So we see we are using 5 volts, 0.08 amps, that is 80 milliamps. So I'll place it around there, place it like so. You get the point? That's it. So I'll switch off. So the whole thing goes off. So that's it for a power supply. That's it. Let me try to power another device for you guys before we go. I'll change the device. So I'll unplug my clips. Alright, put that aside. Let's say we have a more complex circuit now, like this device right here. So I'll place the ground clip to the negative side of the circuit. Then if I place the positive, I switch on, make sure I switch on, so that I can tell whether the voltage is set to the right value. Alright, since it's already set, so you see the device coming to life. See? It's all powered. So let me switch off. And the device goes off. So that's it with the lab bench power supply for now. Section with 2 interesting tools. These tools are too detailed. I will not even demonstrate what they do in this small section, but we will get to learn what they do and how we use them in their respective lectures, where we will have to work with real circuits. So essentially what we have on the table lastly is what we call a waveform generator. So this one happens to be a DDS signal generator / counter. So what this device does is to create different electrical waveforms like sine waveforms, square waveforms, DC, rectified voltages, and very many other types of signals. So let's say we are working on a power conversion circuit. We need to generate a specific scenario whereby, let's say, we are manipulating voltage or current, and we need to use a certain signal type. This will be the device for such a job. This is the tool. Like I said, these two tools go hand in hand and they're a bit detailed, so I will not lengthen this lecture by demonstrating what they do. If I'm to teach them, they require a different series of lectures altogether. That is not the major point of us having this power electronics course. So tools aren't the course unit. Power electronics is the course unit. So I will not dive deep into what these two devices do for now. We will just do that kind of indirectly through the consequent lectures. This one, on the other hand, is what we call an oscilloscope. It's a digital oscilloscope. Think of it as a multimeter. That means it can measure voltage, current, and other electrical properties and more. But it has the ability to put it all on a graph. It has that screen. It has the screen. It has a screen where it can graph a lot of things. So it can take inputs, then graph them voltage against time. So we will see what these do. We will see what these two devices do. So this is a digital oscilloscope, DSO. This is a signal generator, digital signal generator. So here is an in the next lecture of materials that we are to use in this course unit. So let me roughly go through what each and every component is named like and its basic functionality. All right, so I'll start over from the right side. So what I'm holding here is what we call a pair of jumper wires. So their task is to extend electrical connections from one end to another. Nothing much to them, but they're very, 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 very useful. So that is not the only kind of jumper wires we have. Let me extend this a little to the left. So we also have this type of jumper wires. This is the other type. So these ones come in assortments like so. In assortments like this. So this is how they look like. They also do the same job. I'll put that one to the sides. All right. So what we have here, this is a pair of power transistors, right? Power BJTs, right? Look at the back, look at the front, with the leads, the base, the collector, and the emitter. Yeah, we will look at these like I promised. So we know in this course unit we are going to be using semiconductor devices to manipulate power, that is manipulate voltage and current using semiconductor devices and passive components. So this is one of them. This is the other. This is a power MOSFET. All right, we use semiconductor devices in this course unit mostly as switches, not as amplifiers, but mostly as switches. All right, I'll put this one to the sides as well. This is a power diode. Yeah, this is another form factor of a power diode. This is another way of making power diodes. Yeah, this is a really huge one. So what we have on the bench, this is optocouplers. These are optocouplers. All right, so put them aside. So these help us interface low voltage side of circuits with high voltage. All right, okay, like let's say driving transistors. We will look at these in commutator circuits for, let's say, think for devices like thyristors or silicon controlled rectifiers. Okay, we happen to be having our ordinary resistors. This is an assortment of resistors. These happen to be 51 ohm resistors. This is a package of 51 ohm resistors, right? All right, the same goes for this. This is 91 ohms. close to 100 ohms. These are just resistors to control the flow of current and divide voltages around, right? We will see what these are used for. All right, so we have these big boys. We have this big boy right here. We have this is an electrolytic capacitor. This is just a capacitor, an electrolytic capacitor, very huge. We happen to be having a similar capacitor type. Guys, capacitors have types. I don't know, for those who are coming from high school, you may not have covered this, but capacitors are made out of different materials. These are made out of paper. These are electrolytic capacitors. These are made out of ceramic, a material called ceramic or porcelain. So this is it. This is it. This also could be another one. This could be another one. Okay. Electrolytic. So these are just capacitors, right? So they hold charge and dispense it when we need it. All right, those ones to the side there. This is typically found in power converter circuits, right? We'll look at those as well, right, for high frequency filtering. So this is on the output stage of some switch mode power supply. All right, so an inductor is a coil of wire wrapped around a good magnetic material, like in this case ferrite, right? That's one way of making inductors. This is another form of inductor. This is another one, right? Okay, this is another one, another inductor. All right, guess what? This is also another. This is also an assortment of inductors. This is also an inductor. All right, an assortment of inductors, right? A collection of them. This is how they look like. They kind of look like resistors, but there is this form factor, or there is this type of inductors, right? Okay, I'll put that to the side. Okay, this is what we call a breadboard, right? This is what we call a breadboard. It kind of looks like a loaf of bread. Sorry, it looks like a loaf of bread, but it has nothing to do with the dough that makes the bread, or anything to do with baking. No, this is simply used to make electrical connections between components using our friend jumper wires, like so. Jumping connections between different points in a circuit, right? We'll look at that. Okay, that's a breadboard. Here is an assortment of transistors, other transistors, right? BJTs, NPN and PN type, very many. So they all come with part numbers. They can easily be identified. All right, that's another assortment. I will put that one to the side. All right, light emitting diodes, right? Light emitting diodes. So this is also another type of diodes. We'll be using them for quick indication that we have signals present at different points in our circuits. So they are of different colors, right? White, green, blue, yellow, and red. All right. LEDs. All right. Power diodes, right? Guys, up to now we've covered. So look at the size of this thing. Power diodes, right? Huge. Full bridge rectifiers. So this is now collection of power diodes on the inside, so that we end up with a DC output with an AC input. We'll look at this now. This is uncontrolled rectifier. We'll look at controlled and uncontrolled rectifiers, okay, probably in a few lectures to come. So this is it. Okay, put that to the side. And finally, this is what we have. We have ordinary generic rectifier diodes, small signal diodes, right? Yes, this is how one looks like. All right. So, guys, this is just a small collection of components. We are yet to use. There are more like triacs, diacs, thyristors. We will look at them in the consequent lectures. So that's it for now. Let's start off lecture 6. Let's start off lecture 6 with a very interesting device, that is the thyristor, a silicon controlled rectifier. So we've officially entered the realm of controlled rectification. Thank you. See you next time.